All right, so we're going to, in this lecture, continue on the topic of visualizing data, and we're going to talk about the principles of effective data in this lecture. Just a reminder, there's going to be another video where I'm going to demonstrate for you how to make simple graphs in Excel and Google Sheets. And also a reminder, now that you finished the previous video, you can get the chart called Biology 1105 Types of Graph Summary, and you can fill it in and create a study guide for yourself about these different types of graphs. Okay, so topic of today, how not to graph. So remember, the purpose of a good data visualization is to make it easy to interpret the data correctly, easy for yourself and for your audience. There are some graphs that can be intentionally misleading, like propaganda, where there's something funny about the graph and it's been done on purpose to mislead people. This particular graph is from the Florida Department of Law Enforcement from about 7 years ago. And look at the y-axis, it's actually reversed. I get very confused. I'm not really sure what they're trying to mislead us about exactly here, but look, the lowest values are at the highest level on the y-axis. I think it's trying to make us think that the law had the opposite effect that it really did. Okay, so today we're going to talk about principles of effective data visualization. There are 5 that really apply to the graph itself. And then I've added a 6th one because another important principle is to provide the reader with a caption that has all of the information needed to interpret the graph. So we'll go through these principles one by one in this lecture. The first principle is to always show the data and ideally the spread or the variability. Here's an example that illustrates this principle. This is from a CBC web application that let you explore polling data in the weeks before the federal election that happened 2 years ago. So this was data from 2019. And the Liberals and the Conservative Party were very close in polls leading up to that election. And so this is a screenshot of this web application where you could graph the data and change different features of the graph. And so this is what the graph looks like by default. And so what you were seeing is a date along the x-axis and then an estimate of how many seats the parties would win on the y-axis. And it's an aggregator of a bunch of different election polls. However, the default option just plots these time series in this line graph without showing the variability or the spread or the uncertainty. However, you could toggle this little setting, confidence ranges, and then this is what you see instead. And so what looks like a lead for the Liberals throughout time in these polls consistently, now that we can see error bars around these estimates, you can see that the estimates for the number of seats that might be won by the Liberals and the Conservatives are actually well within the margin of error of each other. And the definition of confidence ranges for this graph I've printed below, but it is this technical definition that has to do with confidence intervals. And that's something that we'll cover a little bit later in the course. So the point that I want to make here is just that plotting the estimates alone without some indication of uncertainty or spread can be misleading because really it was a neck and neck tie in this series of polling data for the red Liberals and the blue Conservatives. Okay, so more examples of this first principle. Something that you can see more and more often these days, I found, is graphs where what's shown is the line of best fit, but not the data. And so is that a good idea to show? We should be wary. I think we should be suspicious of times where the author shows us the line of best fit, but not the data. And one thing we can do in Zoom is talk about why. So think about for yourself, why is it important to show the actual data and not just the fit line? What are some features that we can visually evaluate as the reader only if we get shown the actual data points? Okay, so on the left of this slide, there are 2 graphs with a line of best fit and its confidence intervals, and they're identical, but they actually come from 2 very different data sets. And so here I've added on the data on top. So what do we miss out on as the reader when we don't get shown the data points? Think about that, and we'll talk about it in Zoom. Here's another example. 3 relationships between Y and X, the relationships are identical, but the underlying data that derive those relationships is not. And these examples are from the one that I showed you in the last lecture called Anscombe's quartet. It's these 4 data sets of Y and X that have the exact same best fit line, exact same means and standard deviations, but totally different underlying processes in the data. Okay, principle number 2, represent magnitude accurately. And so by that I mean good data visualizations make it easy for the reader to visually compare quantities, to judge numbers and compare them to each other. Okay, so here's an example of a very bizarre representation of magnitude. I think this is definitely from last year from some American ABC TV station. Okay, so here's an example we saw in this course that has something funky going on with magnitude. So we saw this graph from an old paper on falls and injuries in cats. And what's funky here is that the data on the x-axis are presented as this numerical scale of number of stories fallen. But look how it lumps the stories from 9 to 32 into one position on the x-axis. So this can be misleading because the assumption when we just look at a scale like this, the assumption is that intervals along that scale should mean the same thing. And so you have to be very careful with doing something different than that, right? Because by default, the reader is going to assume that those intervals mean the same thing along a linear scale. Okay, here's another example of not representing magnitude accurately. If you get into this graph, I don't even know where to start. Okay, this is actually a really common problem of representing magnitude in misleading ways. So this is a real graph from a brochure put out by the British Columbia provincial government in 2004 about how much the government kind of tax dollars were spent on education per student. And so we've got a bunch of different years along the x-axis as different categories. So we've got kind of different academic years. And on the y-axis, we're representing the amount of spending per capita, per student in the province done by the government. Okay, what's misleading here is that this is a bar graph. So by our eyes are comparing the size of the red blocks as representations of magnitude, but they've chosen to start the y-axis at a number that's very different from 0. So it looks like we have this, wow, amazing increase in amount of spending per student over these 5 or 6 years. But this is a much more honest representation of the same data, right? If we're going to use a bar graph, if we're going to use colored area to represent amounts, then the amount of color should truly represent the comparison of the different amounts. And this is what the honest bar graph would look like. Yes, there's been a steady increase in the amount of spending, but it's certainly not that steep. It's not as though like almost no money was spent in 1998, for example. So I hope you can really see the difference and why it's so important to represent magnitude accurately. And these are these two graphs side by side. So same data, but we get a very different visual impression, and the one on the right is much more honest. So just so that you don't have to worry about this issue, something that I recommend is to reserve bar graphs for frequency distributions, occurrence data, and represent numerical values like means, dollar amount per capita, those kinds of things using box plots, dot plots, scatter plots, line graphs. Okay, then you don't have to worry about this issue. So bar graphs, the y should go down to 0. Save them for frequency distribution. Save them for counts of individuals in categorical data. Okay, so here's the graph that we looked at in the last lecture. This is actually a different way to represent data from a graph we saw in the last lecture. Looking at particular well-renowned sprint athletes and their personal best sprint times at the 100 meter as of a couple of years ago. The data is a little bit old. Okay, so this is a different way to represent it. Before I showed you a bar graph, here we've got it as a line graph. But what's suboptimal about the graph here? Have I made the best choices for the data that we're showing? So we'll talk about that on Zoom. Okay, principle number 3, make graphs easy to interpret. It's actually easy to find examples of graphs that violate this principle. I don't even know what this is showing. I don't speak Spanish, but I don't need to speak Spanish to know that this is just an incomprehensible data visualization. Here's an example that's kind of probably something you'll encounter more commonly, I should say. Okay, a pie chart is one way to show the frequency distribution of a categorical variable. Let's say we have like 5 different colors that people could prefer, and I've polled you on which is your favorite color of these 5, and let's say the pie chart shows the frequencies of those preferences in our class. I'm making that up, I didn't actually do that. But here's the exact same data represented as a pie chart or as a bar graph. So I hope you can see right away how much easier it is to see the differences between the groups in the bar graph as compared to the pie graph. The pie chart really obscures the differences. It's really hard to visually measure like the size of those different pie slices, whereas presenting those things as bars makes it very easy to see the magnitude, see the comparisons between them. Okay, so here's another example of a graph that needs to work on this ease of interpretation principle. This is a really interesting graph plotting species of animals and plants around the world that have been named after famous people. And so there's certain famous people that like discoverers of species love to name things after. People like David Attenborough, Freddie Mercury, Lady Gaga has several species named after her. So what we've got is this graph of number of species on the y-axis, and then we've got each bar as a person. But it's not very easy to interpret. We've got a whole bunch of colored blocks here within each person. We're not too sure what they mean. We look over at the legend. Okay, they're different taxa, but it's like a lot of information within each bar, and there's really not an easy way for the reader to make sense of what how the different colors compare and what we should be taking from those different colors. So one way to make this easier to interpret is to show less, to just show a graph of just the number of species per famous person, for example. Okay, here's another example. These are graphs that students in the class chose for kind of graphs that they liked, they sent in a couple of years ago. So they're a few years old. This one is a interesting comparison of Eliud Kipchoge's marathon time compared to a distribution of typical Boston Marathon racers. It's like a histogram, and then we've got Eliud Kipchoge's time plotted on there with that dotted arrow. But it takes a long time as the reader to kind of figure out what this graph is showing. So pause the video and try to figure it out yourself. There are a lot of features here. It took me probably twice as long to figure out this graph as I probably could have. And so we can think about ways to simplify this graph and make it easier to interpret. All right, the 4th principle, minimize clutter and chart junk. So what's chart junk? It actually has a Wikipedia page. Chart junk is features of graphs that don't add anything to the information conveyed. And actually, they make it difficult or potentially impossible to visually interpret the data. So a classic one is making a 2-dimensional graph 3-dimensional just because, right? So it doesn't actually add anything to the important information. And in fact, it makes it impossible for us to like really compare what's going on with this pie graph. So that 3Difying your bar graphs, your pie graphs, that's an example of chart junk. Other examples include things like this patterned background on the bar graph on the left, or kind of shading, varying the shading in this map on the right, but without using the shading in a way that reflects any data, kind of using it aesthetically, but it just detracts from your ability to glean any information. So design elements that don't convey information are chart junk. Okay, here's an example of a graph with some election polling data from some country in Europe from a couple of years ago. And the heads are interesting because on the one hand, they might make it easy for you to identify what each of these kind of voter preference bar graphs, who they represent, but the heads are like on top of the bars, which is the information we need. So the heads could have been put somewhere else, like maybe below each x-axis label, and then we'd really be able to see the differences. I think the magnitudes are actually accurate in this graph. But there's some other junky elements here, like the kind of varying, the shading at the top of these bars. It just makes it harder to visualize what's really going on. It kind of adds extra features that don't have anything to do with the data. Okay, principle number 5 is to clearly identify the axes and include units on the axes labels. So here's an example of propaganda without any axes labels. Forgetting to label the axes is a classic mistake, says every Biology 1103, 1104 TA. But you'd be surprised how often it happens in real scientific papers. Okay, so what we're going to do now is look at a few examples of data visualizations that violate some of these principles and then look at how to rescue them. So here's an example of a visualization put out by the US government. You used to be able to go to this website, and this was an interactive like Adobe Flash visualization, and you could go there, like click on it and kind of play around with it and sort it by these different elements of the graph. Adobe Flash is no longer supported, and so you can no longer do that, but we can look at these still images of it and we can really assess it. So what is this graph showing? It's showing data from a bunch of big US cities, and it's showing how their populations have been changing around the year 2010. So we've got, for each city is like a little row here, we've got these squares, and there's a legend for the squares up in the top right. And so the squares, if they're gains of people, they're filled in. If they're losses of people, it's an empty square. And the size of the square represents how many people were gained or lost. So we're seeing the migration of people into and out of US cities. Which cities are growing, which cities are shrinking, where are the new residents coming from? Are they coming from other cities in the US, domestic migration or international? And then we've got the net change as the last column of squares in each set of cities here. Okay, so there's a lot of interesting information here, but this is really problematic. Like, how do I compare? How do I visually compare like two squares? Like the kind of international migration, the pink square for New York and like the pink square for Miami. Like, what's the comparison between those two things? It's really hard to tell when we're being asked to visualize the sizes of these different squares on different parts of a page. And of course, showing the negatives as these empty squares makes it even harder. How do we compare like the empty squares to the solid squares? Okay, here is the same data set, but in a visually rescued format. So we still have a lot of information here. Now we've got each city is a row, and we've got still the 4 columns. We're showing like increase, a natural increase, I think, is births. We've got births, we've got migration of people from other places in the US, we've got migration of people internationally, and then we've got net change for each city. And look, each one is a bar graph. And so we've got the scales for these bar graphs along the bottom. And we can still use color to kind of highlight the differences between positive and negative changes. And this makes it much more easy to do the visual math. It's much easier for me to compare a value to New York to a value to Miami when they're on this kind of unified scale. I hope you can see that. And when Adobe Flash was a thing, this was also an interactive graph, and you could like sort it by each of these columns. And so that was really neat as well. And you could see that like Americans at that time were flocking to Dallas and Miami I don't know if that's still true today. And you could see that international immigrants were mostly coming to places like New York and Los Angeles. Okay, and then coming back to the original, it's really hard to make sense of what's going on in the original graph. All right, here's another visualization rescue. This is data that a student in this course found and shared looking at gender representation in dialogue of movies. So how many words were spoken in a movie by female characters and by male characters? And lots and lots of movies were analyzed, were quantified, and then the averages were plotted as these bars and shown over time. Okay, so for each year, we've got a single average value. It's an average across a whole bunch of movies from that year. And then we've got some trend lines attempting to show you the trends. But this is really problematic because this is a stacked bar graph and the female data are just like stacked on top of the male. So like, why is there a trend line for the female? Because like the trend line for the female is like, is it the trend line for the female plus the male? I can't really make sense of that. And frankly, with the stacked bar graph format, I can't tell like what is going on with the female, potential change in female dialogue over time, because it's like the height of those bars, the height of the red parts is hard to visually tell when it's all, the bottom level is all over the place. Okay, here's a rescued version. Instead of the stacked bar graph, let's use a grouped bar graph. Okay, so now we've like the female bars all start at the same level. And this makes it really easy to see that over time, we've got variation in the female dialogue, but we don't really see a big change in the amount of female dialogue over time. But we see that males are actually speaking less in movies over time on average. And the other thing we can see, which we could also see from the graph before, is that the male characters speak much more than female characters. And that's still true today, although the gap between the genders is getting narrower. One last thing I would say, because these are means, these are averages of a numerical variable that we're plotting here, not frequencies, I would actually use a box plot or a dot plot to show the data, because for each year we have data from a whole bunch of movies, right? So it doesn't really make sense to show a single bar. We could show box plots. We could show a box plot for the male and a series of box plot for female. And that would show us the spread. Okay, so in the next part of the lecture, I'm going to show a few graphs, and I'm going to show along the bottom the first 5 principles, excuse me, which focus on everything but the caption, because these graphs don't have captions. And these are kind of fancy graphs found from the internet. They're mostly a little bit chart junkier than the kinds of graphs you might get in a scientific paper. Excuse me. And what I want you to do is to evaluate them on those 5 principles and think about, is this graph like successful in communicating something to me? And if it's not, why? What's wrong with it? Which of the principles is it violating? Okay, so in this first graph is looking at the battery life of a bunch of different battery brands. So keep in mind, this is not a frequency table. This is numerical data on average battery life. And so is this an effective visualization? If not, what might be less than ideal about it? What would you change? Okay, here's another example. This is data from the Democratic primary. It must have been in I don't remember the year. Maybe it was from 2019. I don't know if that's true. Maybe it's from 2015 or something like that. Okay, so what's good, what's not so good about this graph? Okay, here's another one that is more aligned with something you might see in a scientific paper. This is data on enrollment at different California state universities. There's a whole bunch of universities in the Cal State system, and we're looking at their enrollments over time. And here's another example looking at US states, and in 2017, how many children were homeschooled in those states. And something to think about, is a line graph the best choice for this data set? Okay, here's another example. This is data on NBA player salaries from 2019. And another example, this is also data from the United States. These are, by state, percentages of adults who are registered as organ donors. And another really interesting graph showing data from countries around the world. So each data point is a country, and we're looking here at climate vulnerability scores in relation to the carbon dioxide emissions by people in that country per capita. So climate vulnerability is some kind of score that has to do with how affected by climate change are the people in that country going to be? How vulnerable is their agriculture, their way of life to being influenced by climate disasters and things like that? And so what's the relationship between how vulnerable people of a country are and their carbon dioxide contributions into the atmosphere? And could this graph be done as a line graph? Why or why not? Okay, so just to wrap up, I'm showing you the 6 principles again here. And what you should do next is watch the video demonstration that I'll post in this lecture playlist, showing you how to make some simple graphs in Excel and Google Sheets. Follow along, practice making those graphs by yourself. You're going to need to make your own graphs for homework number 5, which will be due on Thursday, October 14. I'll see you in Zoom.